One, and we're up, and welcome to Evaluative Clinical Science Rounds. Here are my usual points of etiquette. Number one, mute your microphones. We encourage you to keep your video alive, but mute your microphone, and if you don't do it, Karen will do it for you. Number two is use the group chat function to raise questions. You don't have to type out the entire question. All you have to say is, I've got a question, and then I will then signal you when you should unmute. Number three is, please be gentle on our presenter. It is so hard to come across properly on Zoom. It is so hard to tell a joke and be funny. Number four, please be gentle on me when I mangle your name on Zoom. It is not a sign of disrespect. It's only a sign of my own clumsiness. And fifth point is, let's all hope we make it to 1 p.m. without a technical glitch. Sometimes we do, sometimes we don't. Zoom is full of surprises. Now, our presenter today is Dr. David Fisman, who received his MD degree from Western University, followed by internship and residency training in internal medicine through a combination of the Royal Vic Hospital as well as Rhode Island. His first fellowship in infectious diseases, a second fellowship in healthcare policy research, all combined with a master's of public health in clinical effectiveness, granted through the Harvard system, ending in 2001. David is currently a full professor at the University of Toronto. He is the division head for epidemiology at the Dalla-Lana School of Public Health. He's a staff physician at the Michael Garron Hospital, as well as he's a very active member of the Ontario COVID modeling group. Many accomplishments as well. I was super impressed by over 100 Medline articles, of which he's first author on about a third, senior author on another third. He has a huge following on Twitter, and he has got some of the largest arm muscles I've ever seen. Is this guy really a full professor? It just doesn't show yet. We're all yours there, David, and thanks for being here.
I mean, in my defense, my arms are actually crossed in that photo, so I'm sort of pushing my biceps forward to make them appear larger. In terms of the Twitter thing, that is definitely a mixed blessing, and enjoy it while you can, because I will be departing once the pandemic is over. My two benchmarks were Donald Trump no longer being the president and the pandemic being over, and I think both of those are coming. But it's really nice to talk to you all. Just looking at the names coming in, I see a Western classmate is on there. I see a number of former students. I see at least one current student. Hi, Harris. And I'll just get right to it. So some disclosures. I've received COVID-19 related funding from CIHR and Health Canada. I sit on a couple of advisory boards. This is a new thing for the BioNTech Pfizer vaccine and the AstraZeneca vaccine for COVID. Acknowledgements, I'm presenting work that is mostly mine, but much of it's in collaboration with others, especially Ashley Chute. We work a lot with Amy Greer, a fellow at Public Health Agency of Canada named Ping Yan, Michael Hilmer at Ontario Health, and we've been working with some folks at Canadian Blood Services on serologic work. And those are my marvelous, two of my, I guess, four marvelous doctoral students, JPCC and Chideri. So in the hour ahead, I'll start off by talking a little bit about COVID-19 as an exemplar of the paradigm of emerging infectious diseases, something that is very much following the script, and in that sense doesn't have a lot of surprises up its sleeve. We'll do a quick update on local, national, and global epidemiology of COVID-19. That's actually in the wrong order, backwards. Start with global and then cone down to Ontario. And then lastly, I'd like to talk about something that that has been of interest to me for a while. When I came back to Toronto in 2006, it was really to be an epidemiologist for the Ontario Public Health Lab. And that was via someone who I think most on the call don't remember anymore, named Don Lowe, who was kind of a marvelous mentor and microbiologist. And am I allowed to say shit disturber during ISIS rounds? He was a marvelous shit disturber and very inspiring. And he's unfortunately no longer with us, but I learned from that experience how important test denominators are when you're studying infectious disease data, because what we see is what we test. And I'll give you two examples of works in progress on that front. They're a little bit more in progress than I had hoped, because I was sort of targeting this morning to have some stuff finished up. So I'll tell you where it's going when I finish off. So this is an old picture. This is some kind of systematic review attempt, I guess, by a fellow named Peter Daszak and his group from EcoHealth, looking at emerging infectious diseases. Emerging infectious diseases have a definition that's so broad as to be meaningless. They're usually described as infectious diseases that are either newly described or which are changing in burden or distribution across, distribution in space, which is kind of every infectious disease, because they're all a bit dynamic. But when these folks tried to look at where new infectious diseases somehow defined are popping up, they found that there's sort of this heat map where by number of diseases identified, and these do somewhat emerge in a belt that goes around the equator. But what I'd like to direct your attention to is panel A is zoonotic diseases that jump from animals to humans from wildlife is W. Panel B is zoonotic diseases from domestic animals. Panel C is antimicrobial resistant organisms, many of which are generated through agriculture and food production. And then panel D are vector-borne diseases, which may be zoonoses, depending on whether you consider insects to be animals. So the common theme here is really ecology, how we interact with other species, how we produce our food, how we're changing the planet, and all the action. About 75% of emerging infections are thought to emerge at the human-animal interface. They jump species. And COVID is an exemplar of that. So when we talk about that sort of species jump, invasion by a novel pathogen, a nice way to think about invasion is almost like thinking about growing a garden. You start with nothing and you grow something. In this case, it's sort of hellacious because you're growing an epidemic, but you've started with a seed, which is a new pathogen. And for that to turn into a garden, for that to kind of replicate itself and flourish, it needs fertile soil. And infectious disease epidemiologists quantify the goodness of that soil using a metric called the reproduction number. How many new copies does the disease make of itself before it goes away? And of course, if it makes less than one copy of itself on average before it goes away, it's sort of not a problem. It may cause a small cluster of disease, but that will die out. Once a disease has a reproduction number that's greater than about 1.2, there's a high likelihood that it will invade, and that's what we've seen here. So just to take you back to January of last year, this is almost a year ago now, I believe we became aware of something fishy going on. How did that joke come across on Zoom?
Yeah,
that was a good one.
Was great.
Something fishy going on at the seafood market in Wuhan. Get it? I was at a planning meeting for the European Infectious Disease Congress that was supposed to happen this past April in France. And we were in Madrid, and I was sitting with this marvelous virologist named Mary Horgan, who said, "Oh, have you heard about this funny thing in Wuhan?" That's my very bad Irish accent. And I hadn't heard about it. But of course, December, I think 30th, ProMed had put out a notification about an unusual respiratory disease that was happening in Hubei in China. By January 22nd, this is about 3 weeks later, this article appears in Eurosurveillance, authored by, I think, someone many folks from Toronto will know, Gabriel Leung, who's now the dean of the University of Hong Kong School of Medicine. Gabriel's a marvelous epidemiologist, and he as a team got to do the investigation of the seafood market. And reassuringly, they published this paper on January 22nd. You can see the rapid publication. Our article submitted January 21st, accepted January 23rd, and published that day, saying that the reproduction number for this thing is 0.3. Okay, so we've ducked a bullet. It's this terrible respiratory disease, but don't worry, it has a reproduction number of 0.3. 2 days later, they published a follow-up paper in the New England Journal of Medicine saying that the reproduction number is actually 2.4. So, which has actually been sort of a signature feature of this, this disease all the way along. It has what's called an over-distributed reproduction number, or a Pareto-distributed reproduction number. So most cases are actually not infectious to others, but it's got a very long tail to that distribution. And we see that manifest in super spreader events. And I don't want to go down the aerosol rabbit hole right now, but it's becoming increasingly clear that this is mostly a not very infectious disease, except when it gets into what the Japanese identified in February as 3C environments, closed, close, crowded. And I would add a fourth C, which is continuous exposure. And then you can get very large clusters of people infected. So we got quite interested in this. And Ashley and I, this is a usual formulation for how epidemics grow. And it's nothing special here, except that it shows how important reproduction numbers are. R naught is the reproduction number in a totally susceptible population in the absence of intervention. And if we introduce a new disease, we expect, if we sort of calibrate our clock into bug time rather than human time, each generation, when R naught is operative, we expect the number of new cases to just be R naught to the, well, usually T, here it's I, R naught to the I, where I is the number of the numberth generation. So generation 0, let's say SARS-2 has a reproduction number of 3. Generation 0, 3 to the 0 is 1 case. That's your index case. Generation 1, 3 to the 1 is 3 cases. Generation 2 is 3 squared is 9, 27, 81. That's as far as I can go, unfortunately. But you see how this becomes a little bit disconcerting. 243, I got it. Because exponential growth, obviously, things sort of take off fast and get scary quite quickly. Now, what we did is, we knew the Chinese had newly recognized this disease. We had an estimate of an R of about 2 and change. And they were doing things about it. I think they locked Wuhan down on the 24th of January. So this is just a revised formulation where we have an R effective at some point in time. So, you're growing under R naught conditions for a little while, and then you do something about it. And now the new cases, the subsequent chain of infections is just going to be that R effective times whatever your cumulative infectious cases were at time T. So we can use a really simple formulation like this to look at, what was the reproduction number at time 0, and what is it after they do something about the outbreak. And this was the original map from Annals of Internal Medicine, where the green boxes here are actually not Chinese reports. These were imputed estimates of how big the epidemic must be from a group at Imperial College in London, based on the fact that even though the Chinese said they had 43 cases of this weird disease, it was showing up, I can't remember which countries it showed up in first. I think it was something like Thailand, Japan, and South Korea. But sort of nearby Asian countries were identifying imports. And the folks at Imperial College sort of said, well, it's implausible that you have 43 cases, but then 3 more just happened to be getting on an airplane that day. So, your underlying epidemic must be much larger. So this is sort of a back of the envelope methodology that people use to impute, based on travel volumes, how big the epidemic must be to be throwing off that many sparks to different places. So, we inflated this. I think this was 1,700 cases was the estimate when they were reporting 40. 4,000 was the revised estimate a week later from Imperial College. And what you can see is as they tested people in China, they sort of caught up with the predicted epidemic curve. So these blue dots are reported new infections in China. And we set this thing up as sort of a contour plot, you know, the idea being that, well, what you'd want to see is these dots kind of start to cross lines horizontally, and that would mean that they were bringing this disease under control. And this is probably my biggest thing that I've been very wrong about, is I actually thought, in contrast to some much smarter epidemiologists like Mark Lipsitch and Neil Ferguson, who said this is going to be a global pandemic, I actually thought they had done it. I thought this was nothing more than SARS-1 with virologic testing, which we didn't have with SARS-1. And we were sort of modeling this out, and I actually told one of the classes I was teaching, you know, it's going to be done by March. And indeed, the Chinese epidemic was done by March. You know, this is data that were used for model calibration. The white dots, the red dots are sort of validation data in terms of where it was going. And you can sort of fit a very simple epidemic model to this and see the Chinese were getting things under control. And then, of course, this happened. Vancouver, February 19th, a misbehaving emergency room physician tests someone who hasn't been to China at all for this new disease. And this is a person from Iran, and she tests positive. On the same day in Lebanon and United Arab Emirates, they say, well, we also have some cases from Iran. Iran at this point, I think, had acknowledged that they had about 50 cases of what was then called novel coronavirus. And over the next day or two, a bunch of other countries with closer connections to Iran started saying, we have exported cases from Iran too. So Ashley Chute sort of turned this on its head and did what the Imperial Group had done with China, and started, you know, estimating, well, what's the likely underlying epidemic size in Iran based on the fact that we have cases in Canada? It's not 50. And so that's where this sort of estimate came from, under different assumptions about where you had a case. You know, so the estimate would be something like 20,000 or 40,000 cases if we're seeing it all over the world. This is a graph that I think is quite nice, which is, Ashley had worked previously at Blue Dot, so had become familiar with something called the Infectious Disease Vulnerability Index, which is supposed to be a score that tells you how resilient a society is going to be in the face of an infectious disease challenge. This score, incidentally, has been completely invalidated by the last year, because, as you would imagine, the United States has a very high infectious disease vulnerability index score. And places like, I'm trying to look, like Turkey, for example, have very low scores and have actually controlled things much, much better. But on the y-axis here, we've got ranked outbound passenger volume from Iran. And what you could see here is that the places that you were likely to get cases exported to from Iran were a number of them. Azerbaijan was not yet at war at this point, but these other places were actually war zones: Iraq, Syria, you know, places that had just come through civil wars. So the likelihood that they were going to be able to mount the sort of control effort that China had just mounted was very low. And this is where I think I kind of, this is my very late epiphany, realizing this was not going to be controlled. So we go back to this original graph, and we've continued it, and you now have to put it on a log scale. You see our green dots from the beginning, where we're sort of pushing 70 million counted cases globally, with about 1.6 million deaths. And this is just the same thing, just showing the case fatality, which is the number of deaths in red here over the number of cases in blue, again on a log scale. So you can see the case fatality went up sharply in spring as this hit North America and Western Europe very hard. In particular, it hit a lot of long-term care homes in both North American and European countries. And now it's sort of settled back down, both as testing has expanded and also as people have learned how to sort of keep this away from those settings somewhat imperfectly. We can look at this in terms of reproduction numbers. Again, this is reproduction number as you know, the Chinese get it under control. This initial red hump on the left here is when this hits North America and Western Europe. You've got a reproduction number on the right side here of about 3. Since that time, reproduction numbers, we've learned as we've sort of locked things down and distanced from each other, we've seen that this actually is, it's very easy to bring this reproduction number down quite low. But of course, to get this to stop, you need to bring it below 1, and we haven't really done that. So over the summer globally, things were at about 1.5. At the end of the summer, dipped down towards 1. And then this is actually our fall wave here, is a reproduction number globally of 1.1 or 1.2 has created this tremendous wave because the number of prevalent infections is now high. So exponential growth operating on, you know, a few 100,000 prevalent infections creates a lot of new prevalent infections. What you can see here is we've sort of, it actually looks like globally this second wave is peaking now. We're at around 600,000 counted cases a day. We'll circle back in terms of what fraction of cases that's likely to be. Yes?
All right, and we've got our first question from Michael Schul. Michael, go ahead and unmute.
Hey, David. Thanks for your talk. Great, very interesting so far. Quick question, or I hope quick question. You're talking about the reproduction number, and you mentioned the overdispersion earlier, and that you didn't want to get into sort of super spreader events. But I just want, I mean, one thing that I'm curious about is you describe the conditions of events that may render them super spreaders, but how much does it have to do with the patient, the infected patient, him or herself? In other words,
a lot.
Yeah, and what do we know about that?
Very little, but it has so I don't have it in this talk. And if any of you have connections at a journal, because we're struggling a little bit with this, there is a marvelous grad student in engineering at U of T by the name of Paul Chen, who has done what I think is absolutely first class work, where he's done a systematic review of viral loads by time in individuals, both symptomatic and asymptomatic. And he's created this database, which is really neat. And then he's modeled that out. He sort of comes from a bit of a physics background. So he and his supervisor have modeled that out in terms of what the implications are for spread. And the high likelihood is what you're seeing here in terms of infectivity is there's a log normal distribution in terms of viral loads. They peak, you know, in the interval between about 1 day before symptom onset to about 5 days after symptom onset. You have average viral loads are highest, but average viral loads are actually not that high. So what you're probably looking at is the folks who are on the tail of that viral load distribution right in this window. And I think this has really important implications. I don't want to get off in the weeds, but I think this has super important implications for infection control, because the folks who are coming into hospital are mostly way along, you know, are a week, 2 weeks on in terms of their clinical course. And I think that's why we haven't seen hospital outbreaks all over the place. I mean, we've obviously got some, we've got 100 or so people in London, Ontario infected, but we don't know that that came from patients. And in fact, if you look in this on the to-do list, if you look in the Ontario data, if you look at outbreaks, it seems like to me, and I've kind of messed with this, and I'd encourage others because I think you'd have access to this data, there's directionality to transmission in hospital outbreaks that looks like it goes from carers to patients, carers to carers, but not patients to carers. And I think that makes a lot of sense in terms of where patients are in their clinical course. You know, they're far along. So no, we don't know. But, you know, and this is a different talk. It's not the talk I put together for today, but there's this phenomenon that one sees with COVID arriving in a new place. And I've likened it to when you try to start an old outboard motor or start an old lawnmower, and you pull the string 6 times and nothing happens. And then the 7th time something happens and the engine turns over. And, you know, who knows what's magic about that? This is 7th time. But I think you're seeing that with this, where we imported cases, nothing happened, we got a bit smug. And then I think we had a missed super spreader event where I believe, and this is not evidence-based, but just in terms of the temporality of this, that we had likely a super spreader event at the Mines and Metals Conference in Toronto that was likely seeded from New York State. And, all of a sudden this stuff is everywhere. But we don't know what makes people different virologically. Kids clear faster than adults, but their average viral load is the same. Sicker people in the ICU clear shedding slower, so they stay PCR positive longer. That's going to be coming out in the annals over the next week or two. But, what makes this person be a 98th percentile person and that person be a second percentile person, we have no idea. I've actually started to call this the Lemony-Snicket model of disease, because it depends on this series of unfortunate events where you have a high viral load individual vocalizing in a close and crowded space, poorly ventilated space.
Okay, that was great, David. We have time maybe for one specific short question with a short answer, and then we'll let you go down.
Sorry.
Harris Majid, why don't you go ahead and unmute?
Hey, Harris.
Hi, Dr. Fisman. So quick question. So out of curiosity, when we talk about these reproduction numbers, so in comparison to the past pandemics like the 1918 and the 1957 pandemic, were these similar?
Yeah, that's a really great question. And that's also something that's in Paul's paper, is what seems to be different about this stuff versus influenza is the reproduction number for influenza is much more homogeneous.
Okay.
It's the log normal distribution in terms of viral load has a much narrower base. So kind of what you see is what you get. It's got a taller peak, narrower base. So an average person is a high viral load person. And an average person looks a lot like the people who are on the 2.5 and 97.5 percentiles of that distribution. This stuff, like a lot of other coronaviruses, like SARS-1, like MERS, there's a lot of skew to that viral load. So the peak is lower and the tail is longer. And that seems to be what's messing us up.
I see. Okay, thanks.
Yeah, no problem. Yeah, no, sorry, I do talk. I'll go on. This is, I'm just going to skip through this stuff. You can just sort of convert things to doubling time from a reproduction number, et cetera. So this is a cumulative case doubling time, doubling about every 2 months at current growth rate, which is actually fairly constant. And you can think about what the implications of that are. If we have 70 million cases today, and we don't see a falling off in growth, which we may start to see, that's 140 million in January, February, beginning of February. This is what deaths are doing. This is sort of a moving average. You can see, even though I've made it a moving average, it's still very noisy. But our second wave here globally is starting to hit, and we're up above 10,000 counted deaths a day at this point. So log linear growth, what are the implications of this? This is that same graph that we made back in February. And what you can see here is that if we sort of put contour lines on here, I think this is a reproduction number that's on average been 1.08 since last spring. What you can see is that this is sort of running parallel to that on a log linear scale. And that makes this very predictable in terms of how many cases we're going to see. We're increasing by about 0.2 log 10 per month. And so if we're at about 7.8 log now, that means we're at 8 log next month, 8.2 log, 8.4 log. And we know we're seeing the tip of the iceberg. This is some stuff that is unpublished and probably unpublishable from this spring, which is just sort of a cumulative meta-analysis looking at serology studies as they started to come out versus reported case counts in different locales. And what you get is, an estimate of somewhere between 5 and 10% of cases are being identified. So let's inflate our 70 million cases. Let's say we're undercounting by 20-fold, which is probably not ridiculous. That would put us at 1.4 billion infections at this point. We have a global population of 7-point-something billion. So once we're getting up around 3.5 billion people infected with this thing for a reproduction number that's 2 and change, we're going to reach a point where this this peaks and starts to decline, whatever we do, vaccine, no vaccine. And that's likely to happen in February, March, sometime around then. It's going to be sped, presumably, by vaccination as well, hopefully. So we can start to think about, where this is going. And that puts us very much on the same time horizon as 1918. So Canada and Ontario, here's our, a tremendously optimistic time in Canada back in August. These are cumulative epi curves. I haven't really done a particularly good job here with the scales. The scales are getting bigger and bigger and bigger. But you can see sort of this rank ordering in Canada, where Quebec has had the biggest epidemic in purple, followed by Ontario, followed by Alberta, followed by British Columbia. This is what things looked like at the end of the summer. And all of these epidemic curves are sort of flattening out nicely. And we all got very happy that, we'd figured this out and it wouldn't be an issue. And this is about a month later, of course. Something magic happened, surely not school opening, because we all know that children are magic and have special unicorn powers that chase the virus away. So it can't have been that, but something else seems to have happened in early autumn that resulted in a resumption of exponential growth. This is epidemiologically unimportant, but I think is going to be a big media headline when Ontario's case count crosses Quebec's case count. And what you can see here is this terrible situation, for example, in Manitoba in light green, which was doing great in the first wave, and is now visible on this graph, as is Saskatchewan, British Columbia, and Alberta. Obviously, both have this nasty concave upward appearance to their epidemic curves. Our reproduction number in Ontario has been hovering around 1, where depending on how we calculate it, what data we use, this is from the IFAS data set, inflated for reporting legs. We estimate that right now we're at 0.9 provincially, so a little bit below 1, with a lot of heterogeneity. So Peel looks very different from Kingston, for example, with much of the province somewhere between those poles. We've seen some changes in recent weeks. Over on the left-hand side are just some graphs in the top panel on the left is what we observe in terms of cases when the Toronto Star says, new record for case counts or what have you. This is what they're talking about. These are the cases that get identified through testing. This is an Ashley Chute graph, which you can tell because it looks nice. It contains a lot of information. And it's sort of on a red to blue scale here, where red is the youngest and then blue is the oldest. And you can see that there's a fair bit of difference in cases per 100,000 per day, incidence from youngest to oldest. If you look at testing, though, what you see is that the oldest people are getting tested the most. This kind of funny parabola here is when we tried to do a lot of school testing and broke the test system, and then that declined. It sort of reminds me of the scene with the bunny at the end of Monty Python and the Holy Grail, where they sort of attack the bunny and then they run away. So we weren't able to sustain this. So we've started to lean fairly heavily, because there's so much variability in testing, and that drives what you see in terms of case counts. Percent positivity is actually a nice metric here. So what you can see, interestingly, is this is young adults here, this orange and darker orange, sort of 20 to 40-year-olds. This is the 40 to 50-year-olds in yellow, and this is little kids. Sorry, have I messed that up? No, yes, I have. This is 10 to 29-year-olds. That's better. 10 to 29-year-olds on the top here, and they've been leading the charge all the way through the summer and continue to do so. These are the 30 to 39-year-olds, so potentially parents and kids. And I think this may be a school phenomenon. And here you have probably self-protective behavior in older people who are really staying out of circulation and have lower per test positivity. And we'll see, if I hopefully get to it, we'll see that reflected in the serology data, actually. But what you can see is we sort of seem to have peaked, and I presume that this reflects some of the very aggressive measures that are currently in place in some of Ontario's hotspots. So this is sort of a happy sign here, where we do seem to have declining percent positivity, or at least flattening percent positivity. There's been a lot of chatter. Dr. Redelmeyer mentioned social media. Of course, there's this whole idea that this is just a case-demic manufactured by, I think it's Bill Gates and George Soros who pay me, and then I I amplify this and receive my check on a bi-weekly basis for doing so. And the evidence for that is that, if we look at our epidemic curve, our day-by-day epidemic curve, we had many fewer cases in the spring, but we had a lot more people admitted to hospitals. That's the third panel from the bottom here, and a lot more people admitted to ICUs, which is the bottom panel. But the key to this, I think, is probably this top panel, which is the average age of cases, which again has gone down and down and down over time and then sort of flat. This is when we really got hit back in April, when we had a lot of long-term care outbreaks and we had a lot of older people getting infected. As that has declined as a fraction of the population, this is over the summer when infection really moved into the 20 to 40-year-olds and sort of disappeared. Little kids weren't at school, older people had gone to ground, and mostly this was an infectious disease of 20 to 40-year-olds. That's declined a little bit in the fall, but not very much in terms of a larger share of infections being in older individuals. And that's important because you have dramatic differences. This is case fatality from a logistic regression model. So these are sort of based on both age and comorbidity. And I think sex is in here too. But these are individuals' predicted case fatalities outside long-term care and inside long-term care in the spring. And you can see the very, very low case fatality in younger people. I've done a terrible job with the x-axis here, which is going from 0 to 9 up to 80 plus, the same age group. So you get this sort of exponential increase in risk of death conditional on infection. And that's been sort of borne out as serology studies have come online. This is an old figure from us messing about with the hollow boxes or some Ontario estimates from Canadian Blood Services. And these are from sort of Spain, Sweden, Geneva, Switzerland, and so forth, where you have this very, very consistent pattern of a log linear increase. This is log infection fatality ratio in percent with age by tenure age category. So, I mean, last week, I think they had a 20-year-old die of COVID in Manitoba. This is obviously not something we want spreading tremendously widely in the community, but the per infection risk is dramatically different for those over 50 and particularly over 60 than it is for younger individuals. What we do see with this increasing age of infected individuals is quite a change in ICU occupancy. This is from Canadian Critical Care Society. This is about a month ago, is Remembrance Day, November 11th. And you can see that many provinces, this is provincial occupancy, we've gone from about 300 to pushing 600 people in ICUs in Canada. In Western provinces, particularly in Alberta, and a little bit in Manitoba. Manitoba is actually on its way back down from about 56, I think is where they peaked. And they've sort of locked down and are doing better. Here in Ontario, we've had a slow but inexorable climb. And we've gone from 80 about a month ago to 213 was yesterday. We have about 600 beds, I believe, left in the province that we could fill. And whether or not we get there really depends on how fast this grows or how slowly this grows. So it's very, very nice to see that our reproduction number is sitting around 1. So back to the idea of this as a case-demic. We've got our reduced age here, which I think explains a fair bit of this difference in hospitalization and intensive care hospitalization between a small spring and a big autumn wave. So this is another recently rejected paper for you. We hypothesized that differential ICU burden might be explained by increased testing volumes in the fall as opposed to the spring. It's easy to forget that in the spring we were testing about 1,000 people a day, and we're hitting 60,000 people a day now. as well as the shift in mean age of cases from older to younger. So these are data that I think many of you will have access to. This is the IFAS and DOLIS data sets. And what we've done here is we've just constructed a very simple negative binomial regression model using only 3 covariates, not a complicated lag structure. It's 2 weeks ago versus now. And if we look at log cases, log 10 cases, log 10 weekly deaths, and mean weekly KJ, and why is this natural log 10 versus natural log? I just thought that doctors would be less scared by log 10 than the letter E, but that turned out not to be true. And we can look at sort of convergent validity with this rule by comparing our estimates of admissions adjusted, transformed into occupancy based on length of stay, comparing that to CHI data, which is a totally separate data source. And what you can see is that there's some nice effects here. The number of ICU admissions that you see in 2 weeks' time is partly a function of cases. So for every log increase in cases, you get a 7-fold increase in ICU admissions, inversely related to the amount of testing you do. Again, this is not a huge surprise. If you're testing more, you're finding more cases, and a smaller fraction of them are going to the ICU, and quite strongly linked to average age of the cases that you do see. And so just sort of going from incidence rate ratio to kind of raw coefficients from the model, dividing those by the coefficient for age to transform this so that age is sort of, you just put age into this little score, and then you adjust these other coefficients correspondingly, and you sort of wind up with this little score, and then you can sort of transform that back into predicted weekly ICU admissions as e to the score times 0.046, which is the smallest coefficient. And it works really well. So this is from about a month ago. The black dots are the ones used to derive the model, and the white ones weren't used for model fitting. We only had 2 extra time points at that point. And if you use a 13-day length of stay, which is about right for Ontario, this transforms pretty nicely into occupancy data. I've updated this for the modeling table. I didn't have the more recent test numbers till just before the talk. So we'll see what the next data point looks, the next sort of projection looks like. There should be 1 more week projection here. But again, the red stuff here is observations that weren't used for fitting the model, and the red is applying that little prediction rule to cases and tests and mean age from Ontario. So this does seem to work fairly well. With a colleague named Todd Lee, I played with this a little bit with Quebec data, and it works miserably in Quebec. So it's not generalizable outside Ontario. What's interesting in Quebec, we think there's probably some sort of funny age, nonlinear age thing in Quebec, where they are very stingy about admitting people to ICUs, and they've been particularly hard hit in long-term care. But both the cases and the tests do work to predict ICU traffic in Quebec, but age doesn't remain in the model. So the kids are all right, mostly. This would be my last brief point, and I apologize because I really was hoping to update this. So kids have such mild illness with COVID for the most part that I can look back to reviewing good papers by good groups in February who were making assumptions in their models, like we left those under age 15 out of the model because they can't be infected with this virus. And it wasn't until, I'm trying to remember what the city was in China that actually went out and tested asymptomatic kids and found that kids were actually infected at fairly high rates. So that's a silver lining here, is that morbidity and mortality is far lower in kids. ICU admissions and deaths do unfortunately occur. They have this interesting hyperinflammatory syndrome like Kawasaki's. Asymptomatic infection in children has been part of this story from the get-go with the original Shenzhen. Oh, it wasn't Shenzhen actually, it was the city where they tested kids. The original family cluster outside Wuhan was reported from the city of Shenzhen, and the presumed index case in that instance was an asymptomatic 12-year-old with an abnormal CT scan, so pulmonary disease and no symptoms. How common that is unclear, but kids do seem to have much milder illness. This is some stuff from over the summer from Ontario. If we look at cases that are listed as asymptomatic, we restrict this to outbreaks because outside outbreaks, people are going to get tested conditional on symptoms, find that kids under 10 have a threefold higher likelihood of being asymptomatic. The smoking thing is also interesting and probably needs to be followed up on at some point. This idea that smokers may have less symptoms with COVID, but haven't had a chance to really circle back, but maybe someone else is interested in exploring that. So if we look at what's happened to our epidemic over time, and this was to July 26th, I believe, and unfortunately I haven't updated this for the talk, but we can see what our spring wave looked like. We can see what happened to testing. We had these dramatic increases in testing over time. And we had a lot of variability in per test positivity, where we were up around 15% in the spring, and then we declined to under 1% over the summer. And we know that what we see is going to be what we test. Let's look at who we test. We can use standardized morbidity ratios and variations on them to explore how differential case occurrence and differential testing may be linked. So what I've done here is I've created standardized morbidity ratios. This is the entire epidemic to July 26. We can look at incidence in a particular age group. This is the 0 to 9s, 10 to 19s, 20 to 29, and so forth. This is by 10-year age category. And then this is the 80 and overs. So we can look at cumulative incidence in that group and divide it by overall cumulative incidence in the population as a whole. And what we should see with a pandemic, if everybody behaved identically regardless of age, because at the get-go, everybody, what defines a pandemic is that we're all susceptible to the pathogen. What we should see is that in all these age groups, it should just follow the straight line, just as the 20-year-olds to the 70-year-olds are doing. We should be seeing that. So this is funny. This is not how a pandemic should look. We should have equal attack rates across the life course. Of course, we look at testing. What we see is that we're over-testing the older people, and we're under-testing the younger people. And when we look at this as per test positivity, it actually looks a little bit less variable than it does when we look at it as standardized morbidity ratios. Okay, so this is this funny observation, is we're seeing a lot of disease and a lot of testing in the oldsters, and very much less disease and very much less testing in the youngsters. And so we can regress these one on the other. So we can look age group by age group. And if we have an SMR and a standardized testing ratio, we can do a little math trick. And we can say, okay, I think SMR is gonna go up as I test an age group more. So I can regress SMR on STR, but I'll do a math trick and turn this into log STR, which will mean that when I'm testing that age group at the same rate the population overall is testing, log 1 is going to be 0. So this is just going to fall out of my regression equation, and the intercept from this model then can be interpreted as the expected SMR in the ith age group if that group were to be tested at the same rate as the population overall. This is not my idea. I stole this. Someone else did this for case fatality. And I've just taken this and applied it to testing and standardized morbidity. But maybe I'll just pause there because I'm talking to folks who are quantitatively better than I am, and see what folks think of that. Does that sort of make sense? Right?
It makes sense, although it's sort of unfamiliar territory, simply because of these enormous sample sizes laid out over time.
Okay. Yeah, and you could imagine doing this at different points in time and seeing it. I mean,
Actually, but just before you
Yeah.
you go on, we'll give one question to Neil Isco. Neil, go ahead and unmute. Neil, you're still on mute.
Thanks. David, I find this fascinating, but the question I have right now is, how do you deal with the person who gets multiple tests? There are undoubtedly patients here who don't represent the whole population, but represent themselves multiple times.
Yes, no, that's an issue. I think in this data set, what we were doing was one and done, you know, so it's just because people can have, you know, their initial test that, you know, their first test is negative, their second test is positive, and then they get a whole stream of future tests that relate to people wanting to see if they're now negative again. So what we had done here was testing, I think in this data set was restricted to the first test for an individual was all that counted. And then we realized that we were deflating test numbers too much. So I'd have to check with Ashley, but I think the current algorithm involves some sort of episode identifier, that all your tests can be, the first test from each of your episodes can be included. So for me, myself, I had a COVID exposure in March, and I was tested, you know, and then I had another test in, I think it was June or July. So I should be able to get both of those tests counted. But if in my test in March, I subsequently had another test 2 days later, I would fall out. But in this one, for, you know, this was the first iteration of this. It's a great question. We just dropped everything after your first test.
Yeah, the previous slide talked about total testing, I suspect. And do you know how many patients, how many people in Ontario have been tested as opposed to not tested, and what the real number of people are?
Not off the top of my head.
Okay.
I mean, there's been a lot of testing.
Yeah. But there's worried well people amongst that.
Oh no, absolutely, absolutely.
Okay. Got it. Thanks.
And now we'll just give one short question and short response to Susan Bronskill. Susan, go ahead and unmute.
Hi, David. Great talk. I have a question about your age group finding. When you talk about the older adults, I'm wondering why you leave long-term care residents in your overall estimates, because we know that sector has been disproportionately hit and have different transmission issues and different testing patterns. So is the spike that you're showing not just long-term care and retirement homes?
A lot of it is, and a lot of this is the long-term care testing blitz, both in terms of the cases and in terms of the testing. Yeah.
So is there not value then in redoing these graphs when you pull the long-term care residents out? So I'm thinking about my own community dwelling parents, right? This is not reflecting their risk at all.
Not for this particular study, because that's actually the point of this study, is we're over-identifying people because we're over-testing them. In terms of the serology stuff that we did, we've done that. The epidemiology is so profoundly different in long-term care that you can't get non-ridiculous results if you leave long-term care in. You get stuff like, you know, you're estimating that we're identifying 100% of cases, because the long-term care cases are so numerous relative to what seroprevalence is from Canadian Blood Services. You know, those are totally separate populations. So you have low seroprevalence in the over 70s in Canadian Blood Services, and then we've got thousands of cases in these elderly people. They're completely separate populations. So there we have not included long-term care for that reason.
Yeah, I just feel like a lot of the public reporting that goes out when it's talking about older adults at risk is just misleading, just because long-term care is having this disproportionate effect. So, you know, the heat maps or anything, I really feel like long-term care needs to come out.
It's a distinct epidemiology, and I refer you back to this. That's why we broke this out. It's different. Yeah, it's different in terms of risk, and it's different in terms of outcome. Absolutely.
Yeah, that's the one age graph I liked.
Okay,
David, David, you've got 5 minutes left. Use them wisely.
5 minutes left. So here is the take home. Is unfortunately, because we're using Canadian Blood Services data, we don't have kids, because kids don't aren't blood donors. But what we can see is we can get these standardized morbidity estimates from serology or from this regression approach, and what we see, which is sort of this brick color, and they actually line up quite well. So we've sort of done this as a bit of an indirect kind of attempt at validation of what we're doing. You've got this sort of funny thing going on with low attack in the 40 to 49s in the blood donor data, but they're not too terrible. Oh, you know what? And this is flipped. This is flipped. No, this is correct. Sorry about that. And standardized positivity, and this is to Susan's question, also actually overlays pretty nicely. But standardized positivity, this is what Susan's talking about, very high percentage positivity relative to tests because of the long-term care outbreaks. So we just sort of did a simple Pearson-like correlation on this, and who cares what the p-value is? But you get kind of nice correlation between the SMR by serology and the SMR by regression, and then you don't with standardized positivity because, as Susan says, the long-term care stuff makes this an outlier in the over 70s. At any rate, humor me and assume that we're capturing more of the older people because they're sicker, so we're testing them more. And we anchor this SMR on older people under the assumption that we're mostly identifying those older people. We can then take that cumulative incidence in older people and sort of adjust and get estimates of cumulative incidence in other age groups to this point, to July 26th in this epidemic, based on the degree to which these groups are under-tested. And so this then becomes sort of a cheap and cheerful way to adjust for under-reporting and underestimation. Where we're going with this is percent positivity right now in Ontario by age group. Where we're going with this, and which what I had hoped to do for this talk and haven't got to it, this has actually been tentatively accepted at ANNLS, believe it or not. And part of what they asked us to do is revise and include this very interesting thing that happened in the spring. So now we've got this massive testing blitz. So if folks have thoughts on how we should approach this, whether we should divvy this time series up and look within different time periods, because here I think we've unfortunately cut off the long-term care blitz over here. But here's the long-term care blitz. You see it in this dark blue here. That was a very different moment in terms of what was happening epidemiologically and what was happening with testing. So whether this should be segmented into 3 different time periods, the back to school, the long-term care blitz, and so forth, and or whether this should be presented as a single entity, I'd love to know folks' thoughts. But that's the next step. And this is to revise it, make it, apparently we are to make it more readable and more clinically relevant and get it back to the journal. But that's really all I had. That's my contact information if folks want to be in touch.
Well, that was great. We're at 12:58, so that maybe we have time for one more question. And people are pinging me privately, but I'll ask the question, but just to harken back to Michael Schul's point about these super spreading events. Is it the person or is it the situation? Is it somebody who's throwing off sparks because of their genetic endowment, or is it with the settings close, closed, continuous, and so forth? What's your stance on that, and how would you ever disentangle the two?
So it's probably, the answer to all of that is probably yes, and that's this Lemony Snicket idea that you probably need a high viral load individual in the right setting, doing the right things, vocalizing, so you sort of have to have these things happening in tandem. We do know what doesn't change viral load. Being a kid versus an adult, it's same mean viral load. Being symptomatic versus asymptomatic, interestingly, same mean viral load. Viral load declines over time, it declines slower in folks who are critically ill, and it declines faster in kids. And that's about all we know. You know, and I have a feeling we'll be trying to disentangle stuff like genetics or comorbidity for a long time to come. But yeah, no, it's heterogeneous, but no idea why. And, you know, there's sort of this usual suspects list in terms of where are these things happening. I mean, most of the population at any given point in time are not singing karaoke or participating in choir practices. And yet around the world, you know, these things are showing up again and again and again and again. And I think it's not just, you know, I mean, the Japanese have the most amazing public health guidance. You know, they reopened their amusement parks. And some of the guidance was, if you go on the roller coaster, do not scream, scream in your heart. And that, you know, that's the only country in the world where people probably actually did that. You know, it was noted early on that the Japanese had opened public transit and didn't have cases associated with public transit. You know, the norm there is you don't say anything on public transit, you look at your shoes. So part of us being kind of a chatty culture and a noisy culture, if you look at, I've learned a lot about aerosol science the last 6 months. If you look at, you know, picoliters of spit that you send into the air, using your vocal cords in different ways, you have log differences, you know, order of magnitude differences in the number of picoliters that you send out into the atmosphere when you use your vocal cords in different ways. It's really interesting stuff.
And on that final a graphical image, we will end. It's now 1:01. Thanks very much, everybody, for being here today.
Thanks for the invitation.
And David, we'll ask you to stick behind for just maybe 1 or 2 minutes as people find that. All right. And we got the recording, and just wonderful.